we're going to move on now to our next presentation, which is the details of actually building the vehicle frame. And so I'll be giving that portion of the presentation. We spent the time yesterday talking about a little, various specialized topics, but now we're going to get to the practical aspects of your design and how you actually put a solar car together. And today we'll talk about the materials that you will use, the roll bar and crush zone rules, suspension and steering, and then wheels and brakes. So when you start looking at the materials that you might use for a frame, the beginning teams tend to use something like mild and carbon steel to start. And we tend to recommend using that up front as an option, not as a recommendation, because it's really easy to work with. With other materials, you might need to get into more detailed type of welding, like TIG welding or other things like that. But with mild and carbon steel, you just use a wire-fed MIG, and you're able to put that together fairly easily. It's very cheap, and so if you had made any mistakes, it's very easy to go and just cut it out and start again. But your downside is that it's going to be heavy, and the picture that you see there is from our 2005 Walnut Solar Car team entry. It was their first year participating in the Solar Car Challenge, and it weighed close to a ton, I believe. We had a nickname for it called El Tanque del Sol because it just weighed so much. We thought that it was a good start to building something that worked, right? It was very easy to modify, but I think in future years we went upgraded to other types of materials. So something that's fairly easy to do. If you had questions about your design, that might be a way to go. A lot of teams like to use chromoly. It's a nice balance between carbon steel, which is easy to work with but heavy, and then aluminum or other composites or things like that, which is more expensive and more difficult to work with. Chromoly is more expensive than mild steel, but it's less expensive than some of the other type of materials. And it does really cut down on the weight, and it really acts a lot like mild steel. It's just that they tend to come in tubes instead of so in mild carbon steel, they come in all different types of shapes, including circular tubes and square tubing. In chromoly steel, they tend to come in tubes, and so that's when a notcher would be helpful in that, to make sure that you are able to cut holes so that it mates well with another tube there, and you can weld it very easily. When you move on to other materials, aluminum is a very common material that solar car teams use as well. What's really nice about aluminum, it is very lightweight as well. And it's very stiff for its weight, so you get a lot of strength there. However, the way aluminum works is it's stiff in one direction along the tube, but it is weaker on if you try to bend it. And so you end up having to put a little bit more material into your frame, and so to truss it appropriately. It is harder to weld than the previous two options because you then have to learn TIG welding. It's just a little more specialized welding technique. With MIG, you can have a single heating element with a wire that feeds out, and so you can just basically point at it and weld. With TIG, you have your element, and then you have a welding rod, and then you have to go and feed that welding rod in without having the heating element touch. And so just something to keep in mind. Just like chromoly, it is generally tubular, and so you want to have something that notches the ends where you attach it to another piece of metal. And then we talked about needing more material because of the way the strengths are. And so certainly a lot of teams have used aluminum, and they do get some nice weight savings for that. But if you choose to use aluminum in your design, you'll want to make sure that you look at the trussing of your frame. Carbon fiber is a nice material that are used by more advanced teams. They are the lightest and stiffest option out there. And then you can essentially create it any shape. So in the picture that you see here, this is what we call a unibody or monocoque design, where they actually use the composite as a way to create structure. And so you see there are certain ribs that are here that help provide for the strength of the car. The thing with composite is that you have to plan this very carefully, meaning you have one chance of creating the plug for it, and then laying out your composite material and vacuum sealing it. And if you happen to have any issues with that, you're basically tossing that whole thing away and starting over. And so we do have a video on our website in the workshop page of a team actually putting a composite body together. And so that might be of interest to you if you're looking at using composites for your car. Because of the way the composites are put together, there are different materials involved, and there's different layering of materials. Composite is essentially a layering of multiple materials. We do require that a professional engineer certify its strength if it's used for the roll cage, roll bar, and crush zone. So something to keep in mind when you consider using that type of material. Of course, a lot of this, we're all talking about tubular frames for the most part. And as you saw yesterday in the Covenant Christian car, you can use same type of materials in a unibody or monocoque design. And so a lot of teams that choose to do that use aluminum and then create their structure from there. And that's an option for you as well. So let's move on to the roll bar and crush zone rules, which is really a big, I think a lot of teams have questions about that. I will say, if you have any questions, please raise your hand up. We've got our hand raised, maybe not. So go ahead and raise your hand, and we'll unmute you for the question. Or if you want, you can also type in the chat or the question and answer, and I will address those questions. Okay, roll cage, crush zone, and roll bar. These are what we mean for these three items, and I'll talk more in details about each of them. But our roll cage is the rigid protection encompassing the entire driver. The idea of a roll cage is that in case of an impact, nothing gets then no part of the impact or no part of your solar car gets impacted into the solar car driver area. So it's meant to be strong, right? It's meant to not bend. And so we do specify minimum outside diameter of the tube and a minimum clearance to the driver to provide them space in case it does bend slightly. Outside of that, roll cage is intended to be the crush zone. And so with the crush zone, you know that, in physics, if you have a force, and if that force is essentially translated directly, then the full force will then transfer to the driver. If you have a crush zone that can take some of the impact and direct that force away, then the driver is then protected. And so these crush zone elements are designed to collapse on impact. And so you see thinner material that's out further from your driver, that as the impact comes, it will then deform and then take some of the force away from the impact. And so the rules regarding crush zone is that it's meant to provide some type of coverage around the driver so that it can deflect it away. And the key here is if you're building crush zone structures, you need to be able to cover the entire driver area. Now, I'll have a diagram for that coming up. Finally, our roll bar is the piece of equipment that protects the driver in the event of a rollover. And so the idea is you want something that's fairly thick and very strong so that if it rolls over and the driver is hanging upside down, they don't hit their head on the pavement, right? Or on something else. And so our rules for that require that it be a continuous piece of metal and that it has a certain vertical distance, meaning that from the top of the driver's head to the bottom of the roll bar, there is a minimum 5 centimeter clearance. There's a particular specification for the minimum outside diameter, so it needs to be fairly thick, and it has to have a minimum wall thickness to provide for that strength. One of the key areas of the roll bar that teams get issues with is that they don't create the roll bar in one continuous piece of metal. A lot of teams at least start submitting their drawings with like a 3-piece of metal with welded together, and so we would provide feedback back that that's not allowed, just because we don't know the strength of the weld. We're not able to X-ray into how well the pieces were welded together, and so it would be difficult to prove that the roll bar has sufficient strength. We do require that roll bar to be welded to the frame, however, rather than attached via bolts and things like that. Okay, so a few details of that. The roll bar example here, you see that there's one continuous piece of metal that goes around the driver. There is a sufficient vertical clearance between the driver's head and the bottom of the driver. And then it's welded down here on both sides. And then typically the roll bar is welded here at the top of the frame and then also at the bottom of the frame. There was a question about whether or not this clearance is with helmet or without helmet. And so if the driver decides to ride with a helmet, which is not required, but and you choose to do so, it would be from the top of the helmet to the bottom of the frame. And so the idea is you want some amount of clearance so that you're not impacting your head on the roll bar itself. The other thing about the roll bar is you see that there in this right picture, a support frame. So the roll bar, you want that roll bar to be supported from moving forward and back. And so this particular roll bar design has it such that they have a vertical piece that is behind the roll bar that ensures that there's no way for it to move back. And then crush zone. We talked through what a crush zone does, but the key part here is it's meant to absorb the impact from either front, side, or rear collision, basically from anywhere that you could be hit. And so we want to make sure that you have structure throughout the car. And we will make sure that you have these structures both via your submissions of your mechanical drawings. And so when you submit your drawings to us in March, we want to make sure that you identify what your crush zone structures are. And then when we get to scrutineering and we inspect your vehicle against the rules, we'll be also checking visually that you comply. And so here's a diagram of the coverage requirements. The area in orange is the area that must be encompassed by the crush zone. And so you see that we have coverage for essentially the entire driver, torso and legs and so forth from side impact. And this is a picture of the side impact view. And so you want to make sure that you provide structure for that. And then, of course, this does not count in the forward and rear structures, which usually isn't a problem because you tend to have structure up front. And then, of course, behind the driver, you have your rear wheel and your structures in the back. And so we tend to focus more on the side where there's really going to be just a frame, right? So here's an example of all that put together. You'll notice that there's a crush zone structure that goes around the car that's fairly thin, and that allows it to take some impact. You see the trussing there to help provide some structure, but yet it's meant to crush. You have one continuous roll bar that goes over the driver's head, and then you have a roll cage that protects the driver all around it. And so I think this is one of a good examples. Another example of a roll cage or crush zone is here. You can see that they essentially used a solid frame on the outside, primarily to capture their solar array. But it would be nice if there was less structure for the crush zone to be able to take the impact. But this particular crush zone would be legal. And then you have some strong material around the driver to serve as the roll cage. And so those are just two examples of the roll bar, crush zone, and roll cage. Okay, I'll pause here because this is sort of one of the key areas of questions or concerns. And so I'll open it up for anyone to bring up any questions that they have. Okay. Of course, if you have any questions, feel free and contact us. One of the things I wanted to bring up while we're on this picture is this picture would have
Wait a second,
issues.
William. There is one question from Brad.
Okay. Let's unmute Brad. All right, Brad, go ahead and unmute and ask your question.
Okay. Our question is, can you hear me?
Yes.
What's the best way to form a continuous roll bar?
A lot of teams get their roll bars essentially bent. There's these way of putting a long tube through a pipe bender. There are companies that do this as well, so you should be able to just essentially roll that roll bar through the bender.
Can I add, William?
Yes.
Sometimes there are shops that even do stuff like automotive exhausts that have the type of benders that can do thinner wall stuff that you can use for the roll bars. I will tell you that as it's specified in the rules, the heavy walls for the roll bars are quite difficult to work with and actually bend. So what you'll likely want to do is request a waiver, explain to us how you're going to integrate your roll bar, and just petition to use something a little bit lighter, something that's a little easier to bend. But as William said, there's vendors you can go to, or like if you don't have that kind of specialized stuff nearby, again, automotive shops usually have these kind of benders if they're going to be working on exhaust. They just can't do super heavy wall stuff. Like you can't do 1/4 inch wall. It's meant for doing thinner gauge exhaust type stuff. So that's one thing to look at, but I would strongly recommend considering a petition for a reasonable size roll bar that you think you can use in your design that you can actually get bent. And obviously aluminum's easier than steel, but you want it to match whatever material your frame is going to be.
Okay. There are other questions. I think let's go from the top there. What material is best for the structures? That particular thing is more of more of what material you're using for your solar car. You want the ability to properly mate your roll bar with the rest of your frame. And so when you consider, if you're building out of aluminum and you make a roll bar out of steel, then it makes it difficult to weld that together. And so you'll want to look at the type of material you're using for the rest of your frame. Now, we do have requirements for the roll bar in different material types. And so you'll want to look at that particular area. There's a question with regard to the thin wire frame. Yes, the thin wire frame would be considered the crush zone structure, though I believe that they have additional additional structure that's out there that helps take in some of the impact. Okay. There's another question about whether or not a square bar be legal for a roll bar. We've just not seen a square bar of that particular size, but I'll let Chris talk to that.
I think the rules specifically call out round. So you do need to use round tubing for the roll bar. You can use square tubing other places on your car. That's just fine. But for the roll bar itself, it should be round.
And then finally, we have a question about whether or not you can have a break in the roll cage and crush zone incorporated into a door that opens and closes. And so we don't say that you have to have a continuous roll cage and crush zone in the sense of the roll bar is the only thing that needs to be a continuous, non-welded piece. But certainly roll cage and crush zone, you can have a break, though I would say that you want to make sure that within the door, you'll want to incorporate a roll cage piece, right? It's some structural components so that when the door is closed, it provides that level of protection for the drivers. Okay.
Joel, you know, you're always throwing the hard balls at us there. Definitely not soft pitching, but this is a good question. The other thing I would add to it is if you do intend to do that, please make sure you submit something to us ahead of time so that we can take a look at it, because I guarantee it'll make a smoother path towards scrutineering. In the past, when we've seen teams that have breaks in the crush zone and the structural frame of the car, we've had judges raise concerns about it. So if you work with us before we get to scrutineering, it gives us a chance to kind of review it and sort of pre-approve it before you get there. Obviously, you know, we're still going to check it out, but I would highly, highly recommend that if somebody, you're going to do a door, you're going to break into the area that's supposed to be protecting your car, email us and say, hey, this is what our plan is. Just want to run it by you. And we'll take a look at it. We may give you pointers, or we'll just give you the thumbs up and say, yeah, it looks good. Bring it to us during scrutineering.
Thanks, Chris. Are there any further questions on this topic? I figure there's a lot of discussion that comes out of that. Okay, one thing I want to note is in this particular example, we talk about the crush zone and roll cage, but just for this particular example, you'll notice that the batteries are in front of the driver at the front of the car. Our rules actually don't allow that anymore, so don't use that as an example, but certainly we're talking about the rigidness of that roll cage around the driver, and that's really the key example of why I brought this picture into the presentation. Okay, the next topic of this presentation was going to be on suspension. I think for the sake of time, I'm going to move that to the afternoon and talk to you about wheels and brakes, and I'll get back to that topic on suspension and steering afterwards, later on in the presentation. And so when we look at wheels and brakes, wheels are one of the more difficult parts of your solar car to source. There's a lot of options out there. And so we'll talk a bit about what type of wheels you might want to get. And then, of course, you have to make the choice fairly early on in the design process. You basically have to start building or designing your frame and seeing how you capture your wheels. And so the options that you have for wheels is you can do a 3-wheel or 4-wheel design. That's the first option, how many wheels. And so if you decide to use a 3-wheel design, you're going to put 2 wheels up front and 1 wheel in the back. We call that a reverse trike configuration. We don't allow for a forward trike, and so you always have to have 2 in front and 1 in the back to provide for proper steering. A 3-wheel design, of course, is lighter than a 4-wheel design because you have 1 less wheel, right? It does provide for easier alignment. You don't have to worry about trying to align 4 different wheels together. And of course, it's less expensive in the sense of you have 1 less wheel. It is, to some detriment, a safety possibility, right? Because in a trike configuration, if any one of the 3 wheels goes flat, you're basically going to be sort of going down on one side or the other. And especially if something happens to your rear drive wheel, that would be a concern. Some teams do alleviate that concern by doing a double rear wheel in the back. And so that allows you to have sort of a 4-wheel type of design in a 3-wheel configuration. and that provides a little mitigation to that. But of course, you get the additional weight out of that. The benefit of doing it that way is added safety, and then you could have a rear end that's more towards the center of your car. You don't have to go have the frame pick up the four wheels on the side. The four-wheel design, of course, is the flip side of that. However, the benefit to four wheels is the safety of this, and we do require this for a cruiser division vehicle. The other benefit we didn't already talk about is that you can straddle dead animals. So when I built our car in '97 and we went to a test of that, we had it where we were on the road and we had three-wheel configuration, and you would see potholes coming out. And you know, if I'm driving a regular car which has four wheels, you want to basically center that obstruction so that you would pass straight through between your tires. Well, I had that in mind as I was test driving, and so I would put that pothole right in the middle between the two front tires. Of course, in a three-wheel design, you tend to put the rear wheel in the center, and so I ended up hitting every single pothole in our test with the rear wheel. And so it's something to think about in terms of the driver and a three-wheel design, is that if you choose to do a three-wheel design, you'll want to have some type of driver training to untrain what you learned driving a regular passenger vehicle and train in the idea that maybe you want to take any obstruction a third of the way over, so that's between the front wheel and the front left wheel, for example, and the rear wheel. Some of the choices that you might have in terms of material are NGM or these I'll call them specialized solar car wheels and tires. A motorcycle, junior dragster, bicycle, moped tires or moped wheels are also a possibility. And so a motorcycle wheel is going to give you a lot of strength, and you're able to essentially just mount them, and you can run an entire race with a motorcycle wheel without having to change it, likely, right? Whereas a bicycle wheel or a junior dragster wheel, it's lighter, and it provides in this particular case, there's even some they call it a little more aerodynamic, and so it's neat to use. And I think that the particular example on the right does provide for a pretty good strength, right? When you talk about like bicycle wheels with spokes, that's when you get into potential issues there with strength, because a bicycle wheel is not really meant to take the stress of sort of side or sort of a bicycle wheel is meant to lean on the axis of the wheel. And so all the forces are right along the axis. And so when you put them in a car and it sort of tilts here and there, but it doesn't tilt fully like a bicycle would, it puts some interesting forces on those wheels. And so I would certainly say, if you are thinking about bicycle wheels, to really talk to some folks to make sure that that's strong. Okay, finally, with brakes, you need two independent braking systems, and that's really the entire chain of the brake pedal to the connector to the master cylinder itself, and then the actual brake calipers. You need two independent braking systems so that in case one is faulty, the other one can still work. Most cars do use hydraulic disc brakes, and we talked about that in the parts presentation. MCP, Martin Custom Products, is a very popular brake to use. We talked about how when you press the brakes in, they actually have some way of, when you release the brake, to actually pull the brake calipers back away from the rotor. And so that's a benefit, that you don't have to worry about the drag, right? In a regular automotive disc brake, it relies on the rotation of the tire or the wheel to back out the calipers. And so you'll always get some drag as you depart as you start up and release the brakes. These particular hydraulic brakes don't do that. And so that's why a lot of people like using those. We've also seen drum brakes being used. Drum brakes could be used, but we tend to see those on the rear wheels, and most people use disc brakes on the front. Brake pedals, let's talk a bit about that. The brake pedals must also be independent. We have, in the past, rules allowed for brake pedals to be linked. And you can see in this way where, pressing the forward pedal will also press the rear pedal, but we no longer allow for that. And so you need to have two independent systems. You can put the brake pedals side by side, but you can't just overlap them. And so we do this because if the front pedal were to get stuck in some way, in this particular example, you couldn't access the rear pedal. And so we require that you have two separate pedals for that. And the brake pedals must be operated by foot. There's no hand brake that's allowed for any of these primary braking systems, the two independent systems. If you choose to have a emergency brake, that would just be a third system. Likewise, a regenerative braking system also won't count as a braking system. There's a question about whether or not front and back brakes count as independent brakes. Certainly, you can have a set of brakes up front that's a pair. That would be one system, and then you could use, let's say, a rear drum brake. So a lot of teams do a pair of disc brakes up front as their first system, and then a rear drum brake as a different system. The concern about that is that we want to make sure that each of those independent braking systems can fully stop the car. And so don't size your front brakes and back brakes so that it's, you need to size them appropriately to independently stop the car. Okay, during scrutineering, we will be doing a brake test.
William, one more quick question that's been hanging out here. Can you remind folks how we can access the recording?
Yeah, I was going to get to that after. Let me just finish this section.
Okay.
The brake test, we will be doing scrutineering, and we will be verifying that your brakes work according to the rules. And so we do that two different ways. We do that statically and we do that dynamically. Statically means that we're going to, when the car is stopped, ask you to push on your car and see that the car doesn't move, that it has enough strength to stop the car, while it's at rest. And then after those tests are all complete, then we will do a dynamic brake test where we will be driving the car at the speed that you intend to drive, and then that'll stop. We'll ask you to brake, and then we'll time your stop and make sure that you can brake in time. So a lot of teams do show up to scrutineering with brake problems, primarily because they haven't tested in advance, and teams that have very heavy vehicles don't tend to put enough braking power in their vehicle to be able to stop something so heavy. Lighter cars is usually not as much of an issue, but as you know, with momentum and force, you need stronger brakes if you have a heavier car. And so that's sort of the end of the first part of mechanical. We will go through the steering suspension portion in the afternoon. Given the time, I'm going to actually continue back onto my building the vehicle frame portion to talk about suspension and steering. Before that, though, I want to address the concept of waivers, and that was hinted at some of the questions and answers that we had. We do have a provision in our rules, 5.21, that allows for waivers to be submitted. And the waivers are really intended to be, hey, I have a particular way of doing a particular design that was essentially in line with what the rules intended to be, but it's not explicitly follows the rules. So, for example, if there's a particular roll bar of equivalent strength that I could show to you, but it doesn't match exactly what the rules require, then you could submit a waiver via Rule 5.21. And there'd be, you would submit the request with the supporting information to Dr. Marks, and then he will then take that under consideration and either issue you an acceptance or rejection of that waiver, or ask for more information. So if there were any rules in particular that you go, well, I think I meet the rule, but not per the explicit metric there, that would be certainly a way to discuss that with us. And so please make sure that you send an email to Dr. Marks with that request, and then we will consider it. Okay, and so let me talk a bit about suspension and steering. It was a larger topic than we had time for at the time. With suspension and steering components, just want to do a little bit more of terminology before we get started. What you see there is essentially a I guess a steering and suspension components, where you start out with the spindle, which is where the piece spins and your wheel is attached to that. And so when you steer, that's what allows things to steer. You have the hub and axle that allows for you to mate that into the wheel. And then you have steering tie rods that allow you to convert the steering wheel inputs into actually steering the car. And so those are the major components. In this case, the axle is on one end or the other end, but you could also have a through axle and get both wheels that way. It's just the axle is the thing that the wheel spins on. Okay. So when we look at suspension types, right, the options that you have are the McPherson struts. They are generally used on our production vehicles. They provide a pretty hefty type of suspension so that you can support fairly heavy cars, but it tends to be heavy, and it doesn't have the level of adjustability. You can't really change the amount of force that the suspension takes. It's basically inherent in the coils themselves. Another option, of course, is solid axle, which basically means essentially no suspension, or there's some of these where there's leaves, right? So there's some level of suspension, which makes things for it to be very simple, but again, it's heavy and lacks adjustability. Most teams essentially go and use a dual A-arm or some type of variation on that. Certainly, there are teams that use a McPherson strut with some type of shock as well, but a dual A-arm is a very common suspension method for solar cars, primarily because it keeps the wheel in alignment. It doesn't sort of rotate the wheel as McPherson strut does. It keeps that vertical, but there's a lot of adjustments there, and so it's something that you'll have to figure out how to do. And so we'll talk a little bit more about the geometries for that. And then, of course, with that, you can mate any type of suspension coil or shock to that. Okay, so steering and suspension considerations. I think there's an animation here that I should have taken rid of. So some of the things that you have to consider when you're designing your steering and suspension is the concept of a contact patch. The idea is when you put your suspension together and you also consider the amount of air pressure that you might have on your tire, you will essentially have a contact patch from your tire onto the ground, right? And so you might say that the ideal situation would be that you have a very small contact patch on the ground. And that's because you want to minimize the rolling resistance that your car produces. If you had a larger contact patch on the ground, you're going to have more surface area that is in contact and produces friction. And so you do want to see if you can minimize the contact patch. But on the flip side of that, your contact patch is what also allows you to steer and to stop, right? That level of friction actually helps you in driving the car. And so you don't want to get to the point in which you have no contact patch or very minimal contact patch, because if you had, let's say, a puddle of water or something like that, that contact patch could cause your vehicle to slide. The other thing we'll be talking about is the steering axis, and essentially your A-arm design can be designed to have a sort of angle to it that allows you to essentially adjust the amount of tilt that your solar car tire has when it goes up and down with suspension. And so we'll talk a little bit about that as well. First off, let's talk about steering geometries. So typically, solar cars, either 3 or 4-wheel design, use something called Ackerman steering. And all that simply means is you want the inner tire of the turn to be turned more than the outside of the tire. And so the reason is, if you look at that turning circle radius, right, you want all the tires to be perpendicular to that so that there's no drag. If there's any misalignment, you'll start dragging the car as it turns. So if you look at that and you look at, well, how does that translate to actual steering? Then if you look at sort of centering that and then making it go straight, you'll see that you'll end up having some steering connections that are essentially pointing to the center rear of your vehicle. And so the way that you make sure everything is aligned properly is that the steering connections where the tie rods attach, point straight to the center rear, and that will essentially translate to the proper steering that you see on the left side. So as you design your steering, please take that into consideration. When you look at the geometry, you've got different configuration angles or considerations. We're going to talk about toe, caster, camber, and scrub radius. With regard to toe is simply the angle of the wheel and tire pointing away from the center line of the vehicle. And so when you look at that, you have the center line of the vehicle. If you're looking top down, you have your neutral, basically that everything's in alignment as you go forward. And then you have your in and out configurations. So if you are trying to figure out your toe, if you have it neutral, you will essentially not be dragging the car down the road if you're going straight, right? Think about this. You have a tire wheel that goes exactly straight and you're driving down the road straight. Your wheel will just go straight and there's no drag. If you have any in or out type of configuration, that means that your wheel will drag a little bit. And obviously this is a much more severe configuration on in and out. But if you have it in or out, you'll have some type of drag. Now, some people do, and race cars do, configure their toe geometry slightly in or slightly out, depending on what they want. This is, I think, more useful for solar cars on a track race, where you might say, well, I want to be able to improve my steering response, and so maybe I'll go out slightly, or maybe I will want to make sure that the tire autocorrects going straight, and so I'll do it in. Those are your options, and you can do that. But in solar cars, we tend to try to keep the toe geometry neutral because of the use of our tires. You know, we tend to use fairly thin tires, let's say Bridgestone Ecopias or other very high pressure thin tires, and you don't really want to have that amount of drag essentially break down that tire. So something to consider. When you talk about measuring the toe and the idea of making sure that you have a neutral toe, if that's what you want, you have to make sure that they're aligned, right? And so the way that you would do that alignment is that you would put a piece of material flat against both tires that you are aligning. And then you would go and measure from 2 points the distance between those things. And so you would go and measure your distance between point A and then your distance between points B. And then you would say, okay, are they the same or are they different? And you know, you want to have the same distance across from both of those. And then there's a simple calculation to say, what is your degree in or out in terms of toe? Now, the toe could also be measured by the distance themselves. Okay, the issue though is we've seen teams that don't have a very prescribed method of alignment measure their toe differently. They might go and say, measure from these 2 points the first time, adjust everything and make sure that everything is in alignment. And then the second time they do it, they might go measure from a different location. And so what's important with this is to make sure that every time you measure for toe and alignment, you do it in the same point at this, every time. One of the simple ways to do that is to just get a long piece of something, piece of wood, or a lot of teams use a piece of metal, sort of a sheet metal that's bent, and they have prescribed points on that measuring device that says measure here and measure here. We've seen some sheet metal that has a couple notches on either end of it, and they just put it against the wheel and they measure front of wheel and back of wheel, and that provides that sense of alignment. Of course, the further out you go with your measurement, the more fidelity that you're going to get. So something to keep in mind as you do your alignment. Okay, let's talk a bit about caster. Caster is essentially the angular displacement of the steering angle for the vertical axis, and I have a picture of that. It's just, if you look at the front of the car being on the right, your caster is that connection between your top and bottom A arm, and that's where your pivot will be. If you have a positive caster, then you essentially provide for some sense of straight line stability, because it'll want to revert back to going straight. But of course, it does make your steering wheel feedback more difficult, because you're going to have to put more pressure to make the car turn. So you may consider some slight caster just to go straight down the road, especially on a road race, but you wouldn't want to do too much to prevent you from having to deal with, forcing the car to turn. And of course, negative caster is always bad, in the sense of, making the car want to go squarely on you as you drive down the road. Yeah. Okay, on the other side, we have camber, which is the angle of the wheel and tire with respect to the vertical axis. And so when you look at camber there, you can essentially align your wheel to go from vertical, in or out. So positive or negative. That's really used for cornering, and you're looking at, like, race cars would put in some type of camber in to help the cars corner better. And so I don't think it's very applicable to solar car racing. Most teams, you probably want to have just a neutral camber there. And then finally, scrub radius. I've messed up the highlighting there, but scrub radius is the distance between the steering angle, where the steering angle intersects the ground and the contact patch of the tire. And so that's really the scrub radius distance there. So when you think about scrub radius, if you take a coffee cup or a mug, right, and if you try to rotate that particular mug on just a point, right, that means 0 scrub radius, then it's very easy to turn. But if all I had was the ability to change the angle using my handle, then I have more of a scrub angle, and it makes it more of a radius to turn. And that's really what scrub radius is all about, right? You want to align things so that your scrub radius is as minimal as possible, so that you can lessen the energy it takes to make the turn, and it also decreases the wear on your tire. And so that's really a brief introduction to your steering and suspension. Hopefully that was useful to you.